All right, now we're going to talk about oxidations, starting in section 12.7, about halfway through chapter 12. And we're going to introduce oxidizing agents. 12.7 is oxidizing agents. It's a quick section, but important. We can take alkenes, and we can do a couple different reactions. These are typically oxygen-oxygen types of delivery. Okay, so we can, or an oxygen-oxygen bond, but we can take alkenes and we can do what's called epoxidation. We can form epoxides. We can add, we can do a dihydroxylation. We can add two hydroxyl groups, two alcohols. We can also do what's called oxidative cleavage or oxidative bond breaking. And we can also do this with alkynes. We'll show just a brief reaction where we take alkynes and do this oxidative bond breaking. So the oxidative cleavage, we're going to break the carbon-carbon double bond completely instead of just use it to put an oxygen on. So we'll see what all these mean. Then we can take alcohols and then we can make aldehydes. We can make carboxylic acids, and we can we can make ketones. Okay, so we'll look at each of these in sequence. Okay, so let's look at alkenes first. Section 12.8 is epoxidation. Okay, so it's an introduction. We've shown one way to make epoxides, and that is deprotonation of a halohydrin, right? You take the alcohol deprotonate and it displaces a chloride or a bromide and makes an epoxide. This is a way we can go straight, and actually you can make the halohydrin from an alkene, right? So that's a two-step route. This is a way we can take an alkene and we can add an oxygen to it directly. We're going to introduce a very cool reagent that at first is going to be confusing. This is called meta-chloroperbenzoic acid. Okay, so you'll learn what a benzoic acid is later. It's just an OH instead of an OOH. Okay, but this has this special oxygen-oxygen bond. Okay, I'm always going to draw this way. Okay, the oxygen, the ester carbon-oxygen double bond. This lone pair can interact with that H. Again, we've said this several times. 5-membered rings are favored. Okay, so we can get an intramolecular hydrogen bond. That means it's a hydrogen bond that's in the molecule. Okay, it's not in that's joined up there like that. Okay, we call this M for meta, CPBA, meta-chloroperbenzoic acid. Okay, and that just means meta part is this chlorine is meta in relation to the ester or the perbenzoic acid part. It's not an ester. Okay, so MCPBA, you'll see that a lot, can convert this alkene to an epoxide. Again, right now we're not worried about what's going on here. And what I want you to see is this oxygen came from the one labeled number 4. Okay, you'll see that mechanistically. We'll go over it. And there's going to be a byproduct here, and it's going to be the aryl, the benzoic acid byproduct. We're going to go through this mechanism. Okay. Again, much like other reactions that we've seen, there is stereochemical implications. You can attack from the front, and you can attack from the back. Okay, those happen to be meso compounds. Cis give meso. Okay, but it's syn addition. The oxygen's attacking. It's being added to the same face, and we'll see this kind of mechanistically. So in this case, you get a meso product, but it's syn addition. Okay, I want you to look back at the bromonium. I'll mention that again in a second, but let's go over this mechanism. Okay, It's really a one-step concerted mechanism. It's all how you set it up. So I'm going to draw the alkene like this now, and I'm going to redraw metachloroperbenzoic acid out. I'm always going to try to draw it like that to give you a hint, right? The hint is there's that hydrogen bond there, internal hydrogen bond. Okay. Oxygen, oxygen, heteroatom bonds are weaker. We'll see this again in radical chemistry. Okay, these we've seen it before with NBS. Heteroatom bonds are weaker. Okay, we're going to get an epoxide here. I'm not showing stereochemistry because it's irrelevant, right? That's just a straight bond. It's irrelevant because it's a meso compound in this case. Right now we want to go over the mechanism, and we're going to get the byproduct, the metachlorobenzoic acid. Okay, MCBA if you want to abbreviate it, metachlorobenzoic acid. So let's draw this mechanism. Again, it's one step. I'm going to redraw the alkene down here, and I'm going to draw this MCPBA in this. Basically, all I did was turn it about 90 degrees, give or take, right? And you can write AR if you want. Let's put in all the lone pairs. We'll talk about this in class, as always. There's some different ways to think about this. I'm going to show you 4 arrows to simplify things, okay? We'll talk about a little bit more arrow pushing picture that we could show. The idea here is don't forget what is the nature of alkenes. They're electron rich. They have a pair of electrons that can reach out and grab things. Okay? This oxygen is electrophilic. Okay? That's hard to wrap your mind around at first, but it is. Because think about this whole group. I'm kind of circling it, but I don't want to draw if the cursor is circling there. This aryl CO double bond oxygen, all that is a good leaving group. Okay? And we're going to see that the hydrogen is already associated with this oxygen. So the alkene, remember the bromonium, right? We had the Br2. The alkene, what's it do? It reaches out from the middle of this, so to speak, attacks that oxygen. Okay? As that's happening, what else is happening? As the alkene is attacking the oxygen, this lone pair is going to come over here and form an oxygen-carbon double bond. This pair of electrons is going to kind of fully hydrogen bond or deprotonate. Okay, again, we're going to kind of go over 2 pictures of this. That pair of electrons is going to attack here. The lone pair is already associated, so you could think of it as that lone pair is attacking that H, and this pair of electrons is going up to oxygen. This is a simplification of the mechanism. The electrons go up, attack this H, and then remember, as an alkene attacks, what's happening? You don't form carbocation here, but you have a partial plus left behind. Okay? The oxygen is going to use this pair of electrons that I'm starting this arrow from to attack and form a bond. So you're going to form a carbon-oxygen bond on one carbon of the alkene, and then this is going to form on the other, and you're going to go there. Okay? Very difficult when you first see this, but it's concerted. Okay? In concert. Recall bromonium. Okay, we've seen something like this before. Instead of a bromonium, we form an epoxide. Okay? So let's go over. We'll draw this mechanism a couple more times. Okay. Let's go over a trans double bond. Okay, we said here that this gives a meso. Okay, so cis will give meso, and there's that. But then trans will give enantiomer. So let's draw that out. Let's draw an acyclic trans. I'm just going to write MCPBA because I'm going to draw it out again. And what are we going to see here? So let's redraw our alkene with wedges and dashes. All right, the CH3 is trans. And you can either attack from the top face. I'm going to draw this the same way I just did. Okay. That top face, I'm going to leave the lone pairs. Well, I'm going to put the lone pairs on there. Okay, what happens here? Pair of electrons attacks. These electrons move over. These grab the hydrogen, and that goes there. What do you get? You get the oxygen delivered from the top face. Okay, that is one product. Let's draw the alkene right down here. Same alkene. I'm just going to show, actually I'm going to draw it right over here. Make room. Same alkene. Ignore this. Okay. What happens? Let's just flip this 180 degrees and draw this the same way, though. That's an AR down there. What happens here? Attacks the oxygen. These electrons are moving. And now that's going to go back over there and attack that carbon. Okay, so the pi electrons are attacking the oxygen, and then this oxygen-hydrogen bond is attacking that carbon. Same mechanism, but you get a different product. What is the relationship of these two? They are enantiomers. Okay, 50-50 mix of enantiomers. And then you do get another organic product. It's the byproduct of MCPBA. Just to draw that out. Again, what am I concerned with? I want the epoxide products. I want the substrate derived products. But you should know that forms. Okay, that'd be important in the mechanism for sure. Okay, let's go back to it real quick and make sure I put it in there. Yeah, I put it in there, and so you get that byproduct. Okay, so you get meso with cis, and you get enantiomers with trans. That's epoxidation. That is racemic. Okay, you get a racemic mixture. So what I'm going to do, I'm going to skip ahead just a little bit to 12.15 because this is another epoxidation reaction. I'm going to skip 12.13 and 12.14. I'm going to completely skip those. I'm going to skip a couple sections that I'll come back to. But 12.13 and 12.14, as usual, are sort of application types of sections. They're very interesting. I recommend you read those. But we're going to skip ahead for now to 12.15. And this is called the sharpless asymmetric epoxidation. Okay, Sharpless is a Nobel Prize winning chemist. He developed this reaction and several others. Sharpless asymmetric epoxidation. Okay. So what we just talked about, let's make our alkene a little bit more sophisticated. We're going to put an alcohol, and this is going to be called an allylic alcohol. Okay? Allylic meaning there's a CH2 next to the double bond. That's an allylic alcohol. This is an achiral starting material. And if you treat that with MCPBA, achiral oxidizing agent, you get two products. Top face that we just showed. That's one product. Two products. Then you get the byproduct from MCPBA, the benzoic acid. There's no preference for enantiomers. It's chiral, but racemic, 50-50, right? So you get a racemic mixture. Okay. The allylic alcohol is key, and there's a lot that goes into this. There's no real picture of the model, but all these things are going to interact. You need an allylic alcohol. Okay. Well, again, this is a very tough reaction, but we'll talk about it. We're not going to do a mechanism for these, but let me show you conceptually what can happen. Okay. So we got the achiral allylic alcohol. Okay, we're going to do a negative, meaning we're going to add a single enantiomer. We'll go over all the conditions. A sharpless asymmetric epoxidation that is going to be selective for the bottom face. And you get a single enantiomer of this. And actually, we'll find out that the double bond geometry is important. We'll get to that. Okay. And you can do plus sharpless asymmetric epoxidation. And you get the top face. We're going to, instead of a mechanism for this, I'm going to give you a mnemonic, okay? But what I really want to stress right now is this is enantioselective. We have not seen this yet. Very, very important concept. We've seen a lot of racemic mixtures. We've seen chiral molecules. But we have not seen reactions that give a single enantiomer, okay? So this is enantioselective. It's selecting for one enantiomer. The sharpless asymmetric epoxidation. Asymmetric means it's not giving this quote-unquote symmetric racemic product. Okay, there's asymmetry in this. You get one single enantiomer. Really phenomenal concept, and many people had done this before he had. Okay, but this is a good reaction to talk about to introduce enantioselectivity, and this is done on epoxides. Okay, so what you'll need to be able to do is predict based on this mnemonic that really I'm going to talk about in class, but I'll mention it here. Okay, and so let's represent the allylic alcohol differently. I'm always going to try to, I won't say always, many times I'm going to try to represent it this way. It's a CH3 there. Okay, and what we're going to see is we're going to use our left hand, okay, to make predictions about this. Okay, and the plus and the minus come from the following. So let me show you this. This particular allylic alcohol, the oxidant, instead of MCPBA, okay, I'm shading the oxygen that's going to get transferred. Okay, we're not going to go over an actual mechanism, but all these things combine. Tert-butyl hydroperoxide or hydrogen peroxide, tert-butyl hydroperoxide, titanium isopropoxide, okay, is a Lewis acid, and then we have this molecule here, which is called diethyl tartrate. ET is ethyl, CH2CH3. This is plus diethyl tartrate, and this is the chirality. It's a ligand. Okay, it's a chiral catalyst. This whole thing is a chiral catalytic system. Okay, this single enantiomer right here is going to give the selectivity. So the plus DET makes it a plus sharpless asymmetric epoxidation. Okay, again, the first time you see this stuff, it's going to be confusing. I'm going to give you, I'm going to use my left hand to teach you a way to make predictions of these. But what you get is, you get both technically, but you only get a very small amount of one and a large amount of another. It's enantio enriched. You get about 2.5% of this, and you get about 97.5% of this. It's a ratio. Maybe you don't get 100%. But you get 95% EE. Remember we introduced that concept? The enantiomeric excess, 97.5 minus 2.5, is 95% EE. All because of this chiral diethyl tartrate. Okay? Diethyl tartrate is a very useful thing. You probably heard it. You might have heard of tartaric acid, and etc. Okay, so we can get this chirality from nature, okay, and use it in this system. And I'll let you try to figure out how to make this prediction. But the plus goes to the palm of the hand. Okay? So I'll give you a hint, and then we'll go over it in class. The alkene is your hand, and your thumb is the allylic alcohol. Okay? So you have to line up your left hand the right way. But if you get it lined up the right way, plus is going to go to the palm of the hand. And I want you to remember that. Plus, palm. Okay? So that's the plus one, and then the negative one is just the opposite. I'm going to draw the exact same alkene. Okay, same alkene, negative sharpless asymmetric epoxidation. Same conditions except tert-butyl hydrogen peroxide, titanium isopropoxide, and the only difference is it's minus DET. Okay? The only difference between these two is that they rotate plane polarized light in a different way, different direction. So these are enantiomers, the ligands, negative diethyl tartrate. Okay? If we line up our alkene, the negative is going to go to the back of the hand, the negative part of the hand. Okay? And you're going to get two products. These are the same two products. We're getting 97.5% of this. And 2.5% of this. Sorry, that's an H. 2.5%. That's 95% EE. So it's just the equal and opposite reaction. Again, it's a tough reaction. We're going to go over this in class, and you can kind of work on how you make this prediction. Okay, it talks about quadrants and things like that in the book. Okay, it explains this as well, and you can kind of try to map your hand onto the alkene, and we'll go over that. Okay. So let's do a few more, and I'll probably save a few of these for class, so we don't have to go through all of them here. But let's at least do a couple, and then we'll go from there. So now we're drawing these in slightly different fashion. Okay, this alkene, it's still an allylic alcohol, but it's tetrasubstituted. Okay, so we need to think about that. Those are oxygens. Tert-butyl hydrogen peroxide, titanium isopropoxide. Again, I won't make you give me these reagents, but you should be able to give me negative SAE or positive SAE. Okay, but really you should be able to predict the products. That's the key thing. Okay, so if we line this up, if you map your left hand onto this, the alkene is your hand and your thumb is the CH2OH, right? You can kind of imagine this is your hand and this is your thumb. Okay, kind of a terrible drawing there, but that's the idea. Then the negative is going to come from the top face because it's the back of your hand, the negative part of your hand. The plus would go to your palm. Okay, so the negative would give you this product. Twist that around a little bit. Okay, the CH2OH. It's only that product. And again, for our purposes, we're saying what's the major product. Okay, you might get 2% of the minor, but we want the major product. Okay, so for rings, it's nice to keep it flat and show the epoxide up or down. Okay, for acyclics, it's probably best to rotate them and put them in the plane with the wedges and the dashes to help you kind of draw it. Okay, so I'll kind of walk through this. This alkene, we got to flip our hand around a little bit. Okay, if we want to get our left hand the way we want it to. This is tricky. I'm going to go through this in class. I'll give this as a take home, and I'll say, what product would you get? Okay, so try to work on that with plus. Use the plus diethyl tartrate. Okay, what do you get? And I think we'll stop there. We'll do a few more of these together. Okay, that'll be easier to do it in person. Okay, so we'll do a few epoxides together, and so that wraps up epoxidation, and we will tackle some more oxidation reactions in the next video.